Hi guys, this is Mr. Robeson, working on AP Stats here. Today we're looking at the section 5.5, which is all about binomial experiments and binomial probabilities. And 5.5 is the last section in probabilities. All right, so when does binomial probability happen and what is it? Well, we have multiple trials. So we're doing things over and over and over again, and these trials are independent of each other. So one does not affect the other. There is the same chance of recording a success every single trial. And success is whatever we call success. So like if we're doing something, it doesn't necessarily have to be something good. It's whatever we decide to be success. Like flipping a coin, we usually say heads is success. All right, so this breaks down into 4 essential conditions. And they are binary, 2 outcomes. One we call success, one we call failure. Independent, we have independent trials. Number, we have n trials. It's a fixed number n ahead of time. And success stays the same each time. So we can abbreviate this using the mnemonic device BINS. So whenever you want to do binomial, you're looking for binary, independent, a fixed number, and the same probability for success each time, which we usually call P, probability of success. All right, so here's examples. Flipping a coin 10 times, asking about getting 7 heads. So do we have 2 outcomes? Is it binary? Yeah, we got heads and tails. That checks out. Are they independent? Yes, coin flips are independent. They don't affect each other. N, do we have a fixed number of trials? Yes, 10 times. Does the probability stay the same? Yeah, the probability of, let's see, we're talking about heads, is going to be 1/2 no matter what. So this is binomial. We'll go over how to find the probability later. Now we just want to know, is it binomial or is it not binomial? All right, our probability P here would be, let's see, N would be 10, P would be 0.5, and we're asking about 7 heads, so that our X later on, we'll call it X, the number that we're looking for, the number of successes we want would be 7. All right, next up, taking 8 free throws, asking about making 4. So are free throws binary? Are there 2 outcomes? Well, yeah, we could make it or we could miss it. So that works. Are they independent? Yeah, for the most part. What happens on one of them is not really going to affect what happens on the next one. Is our n fixed? Yep, we're taking 8 free throws. And does the probability stay the same? Well, probably. Probability of making it is going to be some sort of fixed number. All right, so this is binomial. Next up, count the number of red Skittles chosen from a bag out of 12 tries. All right, well, is it binary? So this is where it gets a little tricky. Well, we have red. We also have like 4 other colors, but we could just say all the other colors together are not red. So then we do have 2 outcomes, red and not red. All right, let's see, are they independent? Does what happens when I pick one affect what happens when I pick the next one? Well, actually might affect it a little bit. If we take out a Skittle, we're changing the total number of Skittles. If we take out a red one, we're also changing the total number of red ones. So this is actually a no. All right, our n here was 12, that is fixed. The same probability? Also a no, because the probability is changing. So most of the time these two will both be no's if one of them is a no. So this is not binomial. Doesn't mean we couldn't find the probability. It just means it's not going to be a binomial distribution. All right, so here's an example, which is not binomial. Flipping a coin 20 times, counting the number of tails as success. Well, that would be our n. Do we have 2 outcomes? Yeah, we got heads and tails. Independent, they're coin flips. N, we have our n right there. And those are the probabilities stay the same. Probability of tails always is going to be 0.5. So this is binomial. So this is bi. So it's not A, because we're looking for a not binomial. Choosing a card from a standard deck 10 times, choosing a card standard deck 10 times without replacement and counting the number of hearts. So let's see, our n here is going to be 10. That's usually the easiest one to find. Do we have 2 outcomes? We have hearts. And we could say the other outcome would be not hearts. Remember, hearts is one of the suits of a deck of cards, so that works out. Are they independent? And, well, it says specifically here without replacement. That means once you take a card out of the deck, it is no longer in the deck. A lot of times we say with replacement and we can put things back in. Like down here it says putting it back. And that takes care of the independence because it doesn't change the probability. And the probability of heart will change based on the number of cards in the deck. So this guy is our guy that's not binomial. All right, choosing a card from a standard deck and putting it back 15 times. So once we put it back, that makes it independent and the probability doesn't change. Same with our bag of Skittles down here. Choosing a Skittle from a bag of Skittles, noting its color, putting it back, do this 10 times, count yellow as success. So since we're putting it back, we're replacing it. Without replacement, that's a problem. All right, so how do we find binomial probability? So we'll take a look at an example here. So each child of a particular pair of parents has a probability of 0.25, there's our P probability, of having blue eyes. Genetics says that each child receives genes from each of their parents independently. Telling us independent right there. If these parents have 5 children, well, that looks like our N. The count X of children with blue eyes is a binomial random variable. Well, they're telling us it's binomial. With 5 trials, probability P of success in each trial. In this setting, each child with blue eyes is a success, S. We could call it S. We could also call it blue if we wanted to. And a child with another color is failure. So brown eyes, hazel eyes, green eyes, whatever, we're calling that failure. It doesn't actually mean it's bad. It's just for our experiment, it's failure. What's the probability that X is 2? So that means we would have 2 out of 5 kids that have blue eyes. All right, well, one way to do this would be, well, we got the probability of success times the probability of success times the probability of failure, and the probability of failure. All right, it's independent, so we can do this. So we can do the probability of all these things happening. It's just the product of all their probabilities. That's where independence comes in. That's why we need to check that condition. All right, so that gets us 0.25 to the second, 0.75 to the third. So this is the number of successes we had. This right here is n minus the number of successes. And this would be the probability of failure, which is 1 minus the probability of success. And that gives us our answer, 0.02637. But wait, that's just if the children come in this particular order. How many different orders could they come in? Like we could switch an S and an F here, and a couple different S's and F's, and move everything around. All right, and if we do that, we get different orders. So we need to wonder how many different arrangements are there of these letters. All right, with 2 of them being S's out of 5. Well, we could try and list all of them, but here they are, listed all. All right, but then the question comes, well, how do you know if you have them all listed or not? Well, we're gonna have to come up with a way to count those things. So it looks like we've got 10 of these. So this is the probability of one way, but we have 10 ways we can do it. So what we do is we multiply 10 times that probability, and that gets us our answer. So about 26% of the time we would have 2 kids out of those 5 kids that have blue eyes, according to this. But now the question is, where does this 10 come from? All right, so it's actually called the number of combinations or arrangements here. All right, so the formula for exactly K successes, where our random variable X stands for the number of successes we get out of n trials, would be the number of combinations times the probability of success to the number of successes times the probability of failure. So this is probability of failure. This is the probability of success to the rest of the times, n minus k. All right, so remember, we're going to have k successes. That means we have this many failures. Number of failures. Remember, failures is not really bad, but k is the number of successes. It says right there. All right, well, this number is actually called the number of combinations, or n choose k. We can write it this way. We can write it this way. And like with n over k inside parentheses like that means the same thing. All right, there is a fancy formula with factorials and things like that. You don't need to know it for the AP exam. But it is the top number factorial divided by the bottom number factorial, and then n minus k factorial. It's like this number factorial and this number factorial are the ones on the bottom. All right, and we can explain how this comes about. If you really want me to one day in class, we can talk about it, but not super important now. So now, how many combinations are there of 4 successes out of 10 trials? Well, that means our n here is 10, our k here is 4, so we could say 10 choose 4, or 10 choose 4 like that. All right, and we can calculate these numbers on our calculator if we want to. There is a way. How many number of ways are there for 8 successes out of 15 trials? So n equals 15, k equals the number of successes 8, so it'd be 15 choose 8, or 15 choose 8 written like that. If you've started to notice a pattern, the bigger number is always the number on top. How many number of ways are there to choose 6 successes out of 20 trials? Well, our n here would be 20. Our k here would be 6. So it'd be 20 choose 6 like that. Or 20 C6 like that. All right, let's pull up our calculator here. Where is our calculator? There's our calculator. My trusty calculator. All right, so let's go to math. Go over to PR probability. There it is, NCR. All right, so like for instance, 10, choose 4, will give us 210. All right, so that's how we do it. It's math. Then we go over to the prob. It could be prob or PRB, depending on which calculator you have. Why do I keep writing that? And then it's number 2, I believe, NCR. All right, and then we can type in the numbers. All right, or we could use the built-in function on our calculator to do the whole thing all at once. All right, so the built-in thing is under second, vars, the distribution menu, and then it's a ways down, it's letter A. And this is PDF. All right, so there is also a CDF, so there's a binomial PDF versus binomial CDF. PDF gives us exact, CDF gives us or less. So we'll talk about that in an upcoming couple of slides here. All right, on any given at bat, a batter has a 28% chance of getting a hit. If the batter gets 5 at-bats in a game, what is the probability of getting exactly 2 hits? All right, so we can either have a hit or not hit. So binary. They are independent trials, yep. We have a fixed number, n equals 5, yep. And the probability stays the same, p equals 0.28, yep. So it is binomial. So we could do binomial PDF. All right, our n here is 5. Our p here is 0.28. Our x here is we're asking about exactly 2. So x equals 2. So we pull up our calculator. And let's see, second, vars. It's way down there, so I usually go up instead. Binomial PDF, there it is. Trials, we had 5 trials, 5 at-bats. Probability of success of 0.28. That's a 280 hitter right there. It's not bad. And 2 successes. And we're just pressing enter a couple times here until we get our answer of 0.2926. 2926. Voila. All right, another example. LeBron James makes 75% of his free throws. Suppose he takes 10 free throws in a basketball game. What is the probability he makes 7 or 8? Or, how are we going to do that? Well, let's check as a binomial. So are there 2 options? Yeah, he can make or he can miss. Are they independent? Sure. We have n equals 10 shots, so that works out. And we have the probability of success, p equals 0.75. 0.75. There we go. Got something out of the way there. So yep, that works out. So we're all good there with our binomial. So we're going to do it once with 7. We're going to do it once with 8, and we're going to add them together. So we got binomial PDF with n equals 10, p equals 0.75. And I do want you to always write this out and label it. X equals 7 plus that binomial PDF with n equals 10, p equals 0.75, and x equals 8. So we pull out our calculator, and we're just going to type that in. So second distribution, we could go down if we want. It just takes a while to get there. There it is, binomial PDF. We got 10 trials. We've got 0.75 chance of success, And we want to know about 7 first. Then we're going to type plus, or we can press enter and get an answer, but I like to just do it all together. So plus, second vars again, down to A. One more, there it is. 10.75 and 8. And press enter, and we'll add the two answers together, and we get 0.53. 0.5318, I think it was. But there we go. There's our probability of him making 7 or 8, 53%. All right, one more example. In a bag of 60 Skittles, 10 are red. If you randomly pick Skittles without looking and replace them after each draw, so we're replacing them, what's the probability of getting exactly 2 out of 6 tries? So binomial, yeah, we've got red and not red. Independent, yep, since we're replacing them, it's going to stay the same. And yeah, we're doing 6 tries, that's fixed, yep. Probability stays the same. So the probability here of red is there are 10 out of 60 total. So it's 10 out of 60. We can leave it like that, that's fine. So now we've got a binomial PDF, because we're asking about exactly 2, with n equal to 6 tries, p equals 10 out of 60, and x equals 2 tries. And if we type that into our calculator, we are going to get 0.201. All right, so that's it for the first one here for binomial probabilities. We'll come back and we'll talk about the more than or less than problems and binomial mean and standard deviation.